Okay, so welcome back. Started recording. So last time, so this is lecture 3, right? So last time we did, in the first lecture, we introduced absolute values, and then we proved this Artin-Weber's theorem, and then we stated these two important lemmas, Hensel's lemma and Krasner's lemma. And in the last lecture, we actually proved these two lemmas, right? We proved Hensel's lemma, one version of Hensel's lemma, and we proved Krasner's lemma. And also we gave an important application of Krasner's lemma. So Krasner's lemma, as we discussed last time, there's not much that go into the proof, though it's a very nice proof, and basically we use the fact that all norms are equivalent on a complete non-Archimedean local field. This was the important ingredient. And as an application, we showed that if you have an irreducible separable polynomial, and if there's another polynomial which is sufficiently close to this one, then that is also irreducible, that is also separable. And if alpha is the root of the original one and beta is the root of this sufficiently close polynomial, then they generate the same field extension. K alpha is K beta. This is an important lemma. We will see some applications maybe later. Okay, so let me start presenting today's lecture. Shall I try a different way of presenting? Let's just see. If it doesn't work, I'll go back to desktop. So there is what is called presentation in a window. So how does that work? Let's see this. Can you see the slides? Can you see the slides?
No.
No. So I think this presentation inside the window.
So you are presenting the wrong window. Like, you need to present the window in which the slides are there. You must have had an option of presenting window.
Okay. Now can you see?
Presenting the window in which you are on Teams. If you present the window in which the slides are there, then it will show.
But can you see now? No.
No.
Okay, so let me go back and present the desktop only. That's what I usually do. So let me stop this and let me present the desktop. Is there any advantage, Manav, when presenting using the window than desktop?
No, like not really. Like if you want to just in desktop, if you present desktop, if you go to someplace else. Now, suppose if you go to some other application, we can see a screen. But if you present only the window, then even if we go to some other application, we can see the slides. We can't see something else. That's it.
That's all. So that I don't care. Yeah. I thought maybe if I'm presenting using the window, I can also see the participants. But anyway, this is okay. So now you can see the slide, right?
Yes.
Manav, can you confirm? Yes, yes. Okay, so good. So this is lecture 3. So we will start with another version of Hensel's lemma, and then we will do this p-adic fields. Okay, so not much today, but we will do another version of. So as I said last time, Hensel's lemma has several versions. In fact, there are better versions than what we are doing, but that requires a bit more work, so I will not do it. So last time we proved Hensel's lemma and Krasner's lemma. We also did one application of Krasner's lemma. This is about a polynomial being sufficiently close. So once again, if you have an irreducible separable polynomial f, maybe we also assume monic, and if g is sufficiently close to it, and towards the end there was some discussion about this being sufficiently close. We will see in applications, we don't really, this non-effective results also have applications. We will soon see. Not soon, but sometime we will see. The statement that we already have has very useful applications. And then this G of the same degree, we are assuming G is of same degree as that of F, reduce, and then you can conclude that G is also irreducible separable, and a root of if you take a root of F and a root of G, they generate the same extension. And today we will first do another version of Hensel's lemma. By the way, this reminds me, last time maybe I asked you to verify something, that if you assume discrete valuation, then a given absolute value on the ground field, you can extend to the field above on a finite degree extension. Could anyone try that? Maybe I even gave a formula and said that maybe you can check that this is indeed an absolute value. Could you do that? Okay, did anyone try? Forget whether you did it or not. Okay, maybe at the end we will discuss. Yeah. So today we will first do another version of Hensel's lemma, and this is not from Lang. This version I have taken from Milne's notes, and then we will look at the structure of complete fields. But I will do one more assumption. Up to now, I did not assume that valuation has to be discrete. We will assume that. So we will start looking at the structure of complete fields with a discrete valuation. So first, let's do this other version of Hensel's lemma. Let's start with some basic, very minimal algebra. So as all of you know, what is a local ring? It's a ring with a unique maximal ideal. So call it M. And this is what is called the residue field, right? If you take your ring and if you quotient by the maximal ideal, you will get a field. So this is the residue field of the local ring. So it's a field. And suppose you take two polynomials, f and g, with coefficients from this local ring. Okay, f and g are two polynomials. Assume one of them is monic. Let us say f is monic. Okay. And suppose it is given to you that, so what is the notation f bar? Can someone tell me what could be the notation f bar?
Just take the quotient of the coefficient.
Yes. So reduction modulo m.
K is O mod m, right?
Go mod m, reduction modulo m. Okay. So oh, by the way, this is not A, this is O. This is O by M. So starting with the typo. So a coefficient will be of the form will be in O, and you go mod M. So put bar is plus M everywhere. Okay. And so the f bar and g bar will be polynomials with coefficients in K, because K is O mod M. And assume that they are coprime in Kx, meaning these two will generate the full ring. Okay, that's the meaning of saying they are coprime. So assume f, so f and g are two polynomials, one of them is monic, and assume that the reduction modulo m, these two polynomials are coprime, they generate Kx. So what can you conclude from this? This means OX can be written as the original polynomials plus m times OX, right? That is basically rewriting this, right? So if you take a polynomial in OX, go modulo m, you know that if you take an arbitrary polynomial in OX, let us say h modulo m, you can write it as AF bar plus BG bar. That means AF plus BG plus a polynomial with coefficients in m, you can write h as a linear combination like that, a combination like that. Okay. So this condition implies this statement, and therefore, so you are interested in considering this particular module. So you take the, so again I have written A, so I wrote everywhere A, and then I went back and changed here O, so I will change this to O. So if you take OX by this ideal, the ideal generated by F and G, it's a module over A, right? You agree? A meaning O, it's a module over O, And do you agree that it's a finitely generated module? Suppose you just quotient by one of them, f, and f is given to be monic. Do you agree it's finitely generated?
Yes, like you look at the degree of f and g. Look at the degree of f, then it's generated by 1 x bar square up to x bar for n minus 1.
Yeah. So that's enough, right? And you are using that it's monic, right? So if you take an arbitrary polynomial here, so if f has degree n beyond n, x n plus 1, etc., you can write in terms of f. And here you will use that it's monic. So this is finitely generated because one of them is monic. Divided by just one, ideal generated by one itself is finitely generated, and therefore this is finitely generated. Okay. So this is a finitely generated O module. By the way, since I don't know what all you have done earlier, if I am in this kind of a situation, do you think I'm going to use some named lemma? Yes, I mean, I'm asking not a precise question. There's a lemma that I'm going to use. Can you guess what it might be? Because of this underlined word and because of our starting assumptions?
Nakayama, maybe.
Yes, yes. Okay. So I just wanted to know. So these things you have done in some course?
I have done them in Algebra 2, but Algebra 2 is not a compulsory course, so I don't know, maybe some people might not have done.
Algebra 2 414? No.
No, Algebra 2 is 5101.
Okay, so that's where you have seen Nakayama lemma. Okay, so anyway, so others find out what that lemma is and also see a proof of it. It's not very difficult, but a very, very important lemma. So this is a finitely generated O module, and what this tells you is m times m is the full m, right? From this it follows. So if you take so you have got this identity, and capital M is this quotient OX by FG. So OX by FG, if you apply M, it is OX by FG. So you get this identity from the given condition. Okay, so this is your starting hypothesis, and that gives you this. And what is the conclusion for Nakayama now? Because this is the only maximal ideal here, right? Usually in Nakayama, maybe you apply the Jacobson radical, the intersection of all maximal ideals. So this is the only maximal ideal. So what's the conclusion now? So Manav, you know Nakayama, no? So
what is
some disturbance.
There
I can't.
exists.
Yeah.
There exists something in capital M such that 1 plus A belongs to the Jacobson radical. I think that's it, right?
No, that is just a characterization of Jacobson radical, no? Nakayama lemma will say that if you have a finitely generated module property, then you can conclude something about that module, right?
M is equal to
M is
0.
0. M vanishes. That's Nakayama lemma. Okay. I think what you said earlier may not have a name. It is characterizing Jacobson radical in terms of units. I don't think it
No,
has a
like
name.
over here we can say M equal to 0 because O is local, right?
Correct.
So for in general, if O is a ring,
yeah,
then I think there is a, we say that there exists A such that 1 plus A is a unit. It's something like that.
okay. Fine. Yeah. And yes. So in the local ring situation, everything is simpler. So Nakayama in the local ring situation will directly say that if m times m is m, then m is 0. So what is the meaning of m is 0? M is this module. That means f and g will generate, the ideal generated by f and g is ax. Right? So the answer to y is Nakayama. So in particular, there exists polynomials in OX such that what is the conclusion here? AX is generated, the polynomial, the ideal generated by f and g is full AX. In particular, one is here. One you can write as UF plus VG. Okay, you get this. And I'm going to claim, so right, at this stage you can say that one can be written as UF plus VG, But I'm going to say that you can also assume without loss of generality that degree of U is less than degree of G and degree of V is less than degree of F. From this, it's automatic. Why is that? You're going to say that degree of U is less than degree of G and degree of V is less than degree of F. You can assume that. That's because you have Euclidean algorithm here. So if degree of V is greater than or equal to degree of F, then you can write V as say QF plus R with degree R less than degree F, and you can substitute and you will get similar polynomial. So just check. I mean, this is standard. It's easy. So apply if this is not true, if this is greater than or equal to, if one of them is greater than or equal to, then the other is also greater than or equal to, no? Right? If degree of V is bigger than or equal to degree of F, then this degree is bigger than degree of Fg. Therefore, this also will have to be bigger than degree of Fg. So degree of U will be bigger than or equal to degree of G. So if one of them is greater than or equal to, then so is the other. And there you apply Euclidean algorithm and put that in, and you can conclude that you can assume that these have this property. Okay, so try that. So I'm not giving the detail here. It's just Euclidean algorithm. Okay, so this is the first observation that if you have coprimality of these polynomials after reduction modulo m, then you can lift it, and you are getting this property. F and G will generate, and this extra property is automatic. Okay, this we are going to use. Though this is the crux of this other version of Hensel's lemma. This is all that we need, and there's a uniqueness in doing so. You are getting there's some kind of uniqueness, and let's state that. So suppose f factorizes as a product of monic polynomials. So let's say f equal to gh, f is also g prime h prime, satisfying the earlier condition. So g bar is g prime bar, reduction modulo m is same, and similarly h bar is h prime bar. Then you want to say that g equal to g prime and h equal to h prime. So what you do is you apply the previous observation. So you apply the previous observation. So provided this is given under the earlier assumption, you have a certain uniqueness. Okay, so the statement is if you can write f equal to gh with g bar h bar coprime, and you can also write f as g prime h prime with g prime bar equal to g bar and h prime bar equal to h bar. So in particular, g prime bar and h prime bar are coprime. Under that condition, there is equality. G is g prime and h is h prime. So from the earlier argument, what can you conclude? You know that G and H will generate OX. You know that G prime and H prime will generate OX. You also know that G and H prime will generate, G prime and H will generate, right? Because all those satisfy this condition. Because after all, G bar is G prime bar. So earlier argument, let us apply to G and H prime. Okay, one from here and the other from here. So you know that G bar comma H prime bar, they generate kx because of this condition, because h bar is same as h prime bar. So apply to g and h prime, you can write one as gr plus h prime s. This is the previous lemma, previous observation. That degree of r is less than degree of h prime, degree of s is less than degree of g. Maybe I'm not using that. Okay, so you will get r and s in ox such that one can be written like this. Therefore, g prime equal to, yeah. So what can you say about G prime? G prime is G prime times 1. So G prime times GR plus H prime S. But G prime H prime is what? G prime H prime is GH. So that is G prime GR plus GHS. And this is divisible by G. Right? This is divisible by G. This is divisible by G. So G divides right hand side. So G divides G prime. G divides G prime. And therefore, what can you say if G divides G prime? Do you agree that G and G prime have the same degree?
Yes, because the same way G prime will also divide G, right?
Either that way, but directly you know that G and G prime have the same degree, right? Because their reduction is the same and they are both of them are monic. No?
No, right? Like the leading terms might disappear on taking reductions.
Leading term is monic, no? Monic.
Okay. Yeah.
Okay. So you know that the degree is the same from this condition because of monic, and therefore G equal to G prime. Or as you said, you can argue with G prime dividing G also, but it's easier. Degree is the same. So G divides G prime as they have the same degree. G equal to G prime, and if G equal to G prime, then H equal to H prime. Okay, so H equal to H prime. So what you are getting is some kind of uniqueness. So what is the actual statement? If F can be written as product of two monic polynomials in two different ways, with G and G prime having same reduction, H and H prime having same reduction, and G bar H bar co-prime, then G equal to G prime, H equal to H prime. Okay, so we have done two small lemmas. The first one is under coprimality of G bar and H bar, you can lift it and you will get G and H generating OX. And in this, you have got some uniqueness. This is all that we need for Hensel's lemma. The second version, so this version of Hensel's lemma says if fx is a polynomial, monic polynomial, such that suppose its bar, reduction modulo m, can be factorized as g0 times h0 in kx. Okay. So if you have a monic polynomial and after reduction modulo m, if that is a factor of two things, then so that G0 bar, H0 bar are coprime. So okay, G0 and H0 are already in Kx. Suppose they are coprime, they are monic and coprime. Then you can lift this. So this is a lifting lemma. You can lift and you can get monic polynomials G and H in OX such that F equal to GH. And G bar is G0 and H bar is H0. Okay, is the statement clear? So if after reducing modulo m, if your polynomial is a product of two polynomials, and if those two polynomials are coprime, then the original polynomial can be factored as G times H with the property that G bar is G0 after reduction mod m, G goes to G0 and H goes to H0. And moreover, such a lifting is unique. G and H are uniquely determined and G and H generate OX. Okay.
Sir, in the previous slide, if G and H are coprime, then why should G and H generate K of X, G bar and H bar?
Where in the previous thing here?
Yes.
Why? Saying
it is an assumption, right?
G bar and H bar generate Kx is an assumption.
Yeah,
this is an assumption.
Then, okay.
Are you asking why this is true? That is by the previous slide.
Yeah, that is fine.
Okay, that's the slide. Yeah, please do ask questions. Let's go slow. It is from this result. So I'm not stating these lemmas as lemma. So I'm just starting the proof and wherever we end is the lemma. Okay, so this is the statement, right? M is 0, so Fg is Ax. Agreed, no? This is Manav, right?
Yes, it's fine now. I was just wondering whether it's an assumption or is it something which is somehow true.
Assumption is in the residue field, and this is the result. MS0 is the result which we have written as 1 is UF plus VG because I wanted to put this extra condition. Degree U is less than degree G and degree V is less than degree F. Okay?
Yeah.
So in this case, in order to get uniqueness, again you are using that lemma that one can be written like this. And so that is two lemmas which we are going to use in this Hensel's lemma. So Hensel's lemma is just this. And first thing is this part we have already done. If you can do that, then they are uniquely determined is already done, right? That's a previous observation. if f equal to gh, it is also g prime and h prime with this property, then our previous slide exactly said that g equal to g prime, h equal to h prime. So unique determination is okay, and g and h will generate OX we have already used. That is the very first thing, that if g bar and h bar will g bar and h bar, g bar is g naught, h bar is h naught. So if g naught and h naught are co-prime, which is given here, then g comma h is OX is also a statement that we have already done. So what do we need to do in order to prove Hensel's lemma? So this part is already done. So we just need to do that there is at least one g and h such that f equal to gh with this condition. Okay. By the way, we have already seen one Hensel's lemma. Can you quickly recall what it is? So f is a polynomial with coefficients in O, and we said that there is some alpha naught such that some inequality is there, no? And then, so what was the inequality? Mod of f of alpha naught is strictly less than mod of f prime alpha naught square. Is that correct? That was our assumption, right? Mod of
Yes.
f of alpha naught is strictly less than mod of f prime alpha naught square. Then there is a root alpha for that polynomial in O. Not just that there's a root, we had an algorithm, right? How did the proof go? We defined alpha I plus 1 as alpha I minus f of alpha I by f prime alpha I maybe, and then that we showed that that sequence is Cauchy, it converges to some alpha which happens to be a root. Okay, that was the first version of Hensel's lemma, but there's a corollary to that. Suppose we wanted f of alpha, we wanted alpha naught, that was the starting point. There is an alpha naught such that some inequality is satisfied. Now that inequality is automatically satisfied if f of alpha naught belongs to M, this maximal ideal M, right? If f of alpha naught belongs to the maximal ideal, what will be mod of f of alpha naught? It will be strictly less than, okay, so let's assume it's a DVR. I'm going to prove this for a DVR. And so M is the unique non-zero prime ideal. And in DVR, we have valuations. And what will be mod of f of alpha naught? It will be strictly less than 1 if f of alpha naught belongs to M, right? Also assume that alpha naught is a simple root. So what I'm saying is, assume that f bar has a simple root. So that would mean f bar of alpha naught is 0, which is same as saying f of alpha naught belongs to M. And because it is simple, what can you say about f prime at alpha naught? That will not be 0, right? That will not be f bar prime at alpha naught will not be 0 because it's a simple root. And that means f prime at alpha naught modulus is outside M. So therefore that modulus will be 1. So you are getting that inequality easily in this trivial case. So if f of alpha, if f bar, if after reduction modulo f bar has a root and f bar has a simple root, then our previous Hensel's lemma can be applied. You agree with this? You have a polynomial with coefficients in O, and after reduction modulo f, so take f bar and suppose f bar has a simple root. Simple meaning root of order 1. No multiple roots, order 1. Then previous Hensel's lemma can be applied, and what will be the conclusion? Conclusion will be that f has a root.
F bar has a root, right?
F bar has a root is the assumption, and that Hensel's lemma can be applied, right? What was the earlier Hensel's lemma? If that inequality is true, then by that algorithm you get convergence and you get a root, no?
Yes.
So if f bar has a root, then that root you can lift. So call it alpha naught, and then you can apply that algorithm and you will get a root for f. Agree?
Yes.
So if f bar has a simple root, our earlier Hensel's lemma is applicable, and I am saying you will get a root which will also be simple. You can show again by that Hensel's lemma. So it will be lifted and you will get f to have a simple root. What I wanted to say is that follows from this also. That's a particular case of this result, right? If f bar has a simple root, what does that mean? F bar is g naught times h naught, where g naught is a linear polynomial. That's the meaning, no? F bar has a root. If f bar has a root alpha naught, that means this f bar is x minus alpha naught times h naught. And this would say that it can be lifted so that f equal to gh, where g bar is g naught. So what will be g bar? G bar will be some x minus alpha, where alpha bar is alpha naught. Okay, so what all I'm trying to say is I'm giving another version of Hensel's lemma, but that Hensel's lemma and this Hensel's lemma has the same corollary, which is that if f bar has a simple root, it can be lifted. That's a corollary to this Hensel's lemma. That's a corollary to that Hensel's lemma. So what we have stated as much more general, this is also much more general. And I don't think this implies that or that implies this, but both of them have the same corollary. Okay, so that corollary is what is often called the trivial case of Hensel's lemma. So what is called the trivial case of Hensel's lemma, that one, what we did is one generalization. What we are doing now is another generalization. This, we have almost done this in the previous two slides. So the proof is now easy. So let's do it. So we just need to show the existence of g and h such that g bar is f equal to gh, g bar is g naught, h bar is h naught. The rest we have already done. So we assume O is a DVR, discrete valuation ring. My absolute value is, my valuation is discrete, though the result is true more generally, but then the proof is a bit more complicated. So I will stick to this. Okay, finally, if we are doing algebraic number theory, then we will deal with number fields, and at each prime ideal we will complete, and we will get complete non-Archimedean fields, and all of them are going to be DVR, discrete valuation rate. So our basic interest in this course is only in DVR, not in much more general complete non-Archimedean fields. That's also interesting, but not in number theory. Number theory, only DVRs are coming naturally. Okay, so let's assume DVR so that the proof is simpler. Otherwise, also the result is true. So a field where Hensel's lemma is satisfied is what is called a Henselian field. And it comes in algebraic geometry and various other places. In algebra, people study Henselian fields. And you can show this result is true. This version of Hensel's lemma is true for any Henselian field. So we are assuming that it's a DVR, therefore it's in particular a PID. And M is generated by one element. Let me call it pi. And what we know is that there exists G naught and H naught in OX such that F minus G naught H naught, such that F bar is G naught H naught. So, okay, I'm, slight abuse of notation. G naught and H naught were actually in KX. I'm using the same notation to represent the lift also. Okay, in OX. So what we know is F bar is G naught times H naught. So therefore we know is 0 in that quotient ring, right? So it is in pi OX. This will be a polynomial with coefficients in m, so that when you reduce mod m, f bar becomes g naught h naught. This is what is given to you, and the proof is by induction. Okay, so assume by induction that we have monic polynomials gn and hn in OX such that f minus gn hn is in pi power n plus 1 OX. So this is what is given to you. F minus g naught h naught is in pi OX, and assume that this is induction hypothesis. Assume that you have monic polynomials gn and hn such that f minus gn hn is in pi power n plus 1 OX. So for n equal to 0, it's already given to you. Assume this, and you want to prove that you want to prove the next step. You want to prove that I can get a polynomial, two polynomials, such that f minus the product of those two polynomials will be in pi power n plus 2 OX, n plus 2. Okay, that's what I'm going to show. By induction, this much is assumed, and I'm going to show that for n plus 1, this result is true. So with this condition, Gn is conjugate to G naught modulo pi and Hn is conjugate to H naught modulo pi. Okay. Is there a question? Okay, so let's do this. So we claim that there are polynomials u and v with coefficients in O with degree of u less than degree of g naught, degree of v less than degree of h naught. You will see the importance of this a bit later. Such that f minus one polynomial times another polynomial is in pi power n plus 2 ox. We are claiming this. Okay. So we are saying that. So what will be Gn modulo m? This polynomial modulo m will be what? Yeah, let's analyze that, because our induction hypothesis is you have Gn and Hn both monic such that f minus Gn Hn is in pi power n plus 1 and Gn is after reduction mode pi is G naught, Hn is H naught. Okay, so what we have to show is there are two polynomials such that f minus the product of those two polynomials in pi power n plus 2 with the extra condition that the first polynomial is G naught and the second polynomial is H naught when you reduce modulo pi, reduce modulo m. Okay, so let us analyze. If I take this as my first polynomial, what is its reduction modulo m?
Same as
M is same as pi. Yeah.
Same as Gn
Okay,
reduction modulo m.
And which is what?
G naught modulo m.
Yeah, which is G naught. Yeah, if you start, yeah, G naught modulo m, which is what we call G naught. Okay, but are you using something that this reduction is same as Gn? Yeah, this reduction is same as Gn reduction. That is correct because pi is 0. That is correct. But okay, that is correct. That much is correct. And can you say that this is also a monic polynomial?
Gn was monic, right?
Gn was monic. So is this polynomial also monic?
Yes,
All the Gn
right,
are
because
G naught is monic, all the Gn's are monic. Therefore, the degree of Gn is same as degree of G naught. So this will be monic provided. So this degree is degree of G naught. Degree of Gn is degree of G naught because both Gn and G naught are monic and reduction modulo pi is same. And so this will be monic provided degree of U is less than degree of G naught, which is given to you. I mean, we are going to construct U with this property. Okay, so that's where this inequality plays a role. So that in the induction hypothesis, in induction, each polynomial that you are constructing is monic. Clear, no? That's where you're going to use this property, this inequality, because U has degree strictly less than G naught. The leading coefficient is coming from Gn and therefore it is monic. Okay. So this is what we are going to claim, that there are polynomials U and V with these inequalities such that f minus the product of these two, Gn and Hn are already there by induction, and you are adding something to it, and you are saying that this difference is in pi power n plus 2. So this is what we have to claim. Okay, but then this is equivalent to, you just do this product. This product is Gn Hn minus pi power n plus 1 times Uhn plus Vgn plus pi power 2n plus 2 times Uv. But pi power 2n plus 2, 2n plus 2 is bigger than n plus 2. No, so that part I don't have to write. That anyway belongs to pi power n plus 2 ox. So you agree with this? F minus Gnhn minus pi power n plus 1 times Uhn plus Vgn plus the next term is anyway here. So that I don't have to write. Agree? This is equivalent to this. Which is equivalent to Uhn plus Vgn is conjugate to f minus Gnhn by pi power n plus 1 modulo pi ox. So you are dividing by pi power n plus 1 throughout. You will get a conjugate relation here and you are dividing by pi power n plus 1 throughout. So pi power n plus 2 has become pi, but that makes sense. So that needs a justification. What is the justification for dividing and getting this? What is the justification for this? The justification is that this makes sense. This belongs to O, and this belongs to O because f minus gn hn by induction hypothesis, f minus gn hn belongs to pi power n plus 1 ox. Therefore, f minus gn hn by pi power n plus 1 belongs to ox. Okay, and because of that, this is equivalent to saying this. UHN plus VGN is congruent to this. But this is true. Why? This is true, which is fine. With this condition, with this inequalities. Why is that? Because what you know is, you can write 1 as, right? Gn and Hn have the property that Gn bar is G0, Hn bar is H0. And G0 and H0 are coprime. Therefore, from the very first observation, you can write 1 as something times Hn plus something times Gn with these properties. Degree of U is less than degree of Gn, which is degree of G0, and degree of V is less than degree of Hn, which is degree of H0. Okay, you can write 1 itself like that, but if you can write 1 as that, you can write any other polynomial like that by multiplying by this throughout. Okay, so this is the very first Nakayama lemma argument. So by Nakayama lemma argument, this is fine with these conditions, and therefore by induction you have got this. Okay, so this claim is done. So this is fine by the earlier argument using Nakayama lemma. And now I claim that therefore the proof is done. Why? Because by induction you have come to this stage. Therefore, what have you done? What have you achieved? You have achieved that you have got a sequence of polynomials G0, G1, G2, etc., Gn, etc. with this property. F minus Gn Hn is in pi power n plus 1 Ox. So you have got the sequence Gn. But how do you construct this sequence Gn? Gn plus 1 is Gn plus pi n plus 1 u, where this u is gotten by Nakayama lemma. But whatever that is, it has this inequality property. Therefore, Gn plus 1 is this. So do you agree that the sequence Gn is Cauchy? Because in the p-adic world, in this non-Archimedean world, you have to only look at successive differences for Cauchiness. So Gn plus 1 is this. So what is Gn plus 1 minus Gn? It is this. But this absolute value is small. No, this absolute value is some c power n plus 1, where c is less than 1. And as n increases, that becomes smaller and smaller. Therefore, this sequence, the sequence that we constructed is Cauchy, and therefore it will converge to a polynomial g. Right? Each of the coefficients. So considering a polynomial is same as considering a certain tuple, because each of them have same degree. So it's considering the same R tuple. If degree of G0 is R, it's considering R tuple. So you have got a Cauchy sequence. So it converges to a polynomial G. And from this condition, f minus the product belongs to this. At each stage it happens. Therefore, f becomes G times H. So this is Cauchy by our construction, and therefore you have got convergence. So you get polynomial G, polynomial H, such that f minus GH is in pi power infinity, so to say, which means f minus GH is 0, which means f equal to GH. So that gives you this Hensel's lemma, f equal to GH. And why is it true that G bar is G0 and H bar is H0? Because at each stage, Gn bar is G0. So when you construct Gn plus 1, its bar was G0, etc. So G bar is also G0 and H bar is H0. Okay, so sometimes this is useful. So if you have factorization after reduction modulo M, then you have factorization here. Moreover, you have some control on factorization. You have G bar is G0 and H bar is H0. So factorizations can be lifted to characteristic 0. Okay, that's one way of saying. I have in mind again number fields, p-adic fields, but it can be lifted. Yeah, that's this Hensel's lemma. And as I said, both these Hensel's lemmas that we have proved have this corollary, which is a trivial case of the Hensel's lemma. So both the versions of Hensel's lemma that we have proved are generalizations of what is called the trivial case of Hensel's lemma, which is the following statement. If there exists alpha naught in O such that f alpha naught is congruent to 0 mod m and f prime alpha naught is not congruent to 0 mod m, right? So this means f bar has a root and that root is simple because f prime bar at alpha naught is not 0. So f prime has a, so this statement is nothing but f bar has a simple root. That is this statement. So if f bar has a simple root, then f has a root alpha in O such that alpha bar is alpha naught, and that is because of this condition. Because of this condition, you get f alpha naught belongs to M. And the definition of M is modulus is strictly less than 1. So this is strictly less than 1. Whereas f prime alpha naught is outside M. But on the other hand, f prime alpha naught is in O because f has coefficients in O. Therefore, modulus of f prime alpha naught from this is 1. So this modulus is 1. Therefore, its square is 1. And this modulus is strictly less than 1. Therefore, the Hensel's lemma condition is met. Mod f alpha naught is strictly less than mod f prime alpha naught square. So this is a corollary to that. This is a corollary to this also because this corresponds to g naught being x minus alpha naught. G naught is x minus alpha naught. If you take, you can lift it, you will get g to be x minus alpha, where alpha bar is alpha naught. So it's a corollary to this also. So both are generalizations of the trivial case of Hensel's lemma. How do you get alpha bar is alpha naught from the earlier version? You know that you can lift it and you've got some alpha. Why is alpha bar is alpha naught? Because you know that in that Hensel's lemma also you know that mod alpha minus alpha naught is strictly less than, can someone recall? C, is that true? That quotient f prime alpha naught by f alpha naught by f prime alpha naught square modulus, right?
Yes, that is greater than equal to mod alpha minus alpha naught.
Correct, and that is 0. F alpha naught by f prime alpha naught square, but f alpha naught is 0. So that constant is 0. So what you will get is mod alpha minus alpha naught is strictly less than or equal to that constant, less than or equal to 0, which means it is equal to 0, which means alpha is alpha naught. Alpha bar is alpha naught.
How do you know mod f of alpha naught is 0?
Mod f of alpha naught, sorry. So I'm not saying, sorry. I'm not saying mod f of alpha naught is 0. That's not what I wanted to say. Good, you pointed out. What I'm saying is mod f of alpha naught is strictly less than 1.
Yes.
Okay. Divided by mod f prime alpha naught square, which is equal to 1. So that constant C in Hensel's lemma is a constant which is strictly less than 1.
Yes.
So what you know is mod alpha minus alpha naught, by the conclusion of that Hensel's lemma, mod alpha minus alpha naught is strictly less than 1.
We already knew that, right? Because alpha minus alpha naught belongs to M. So
No. I'm claiming this.
Didn't the Hensel's lemma say something about that? Oh, okay.
F has a root alpha such that alpha is congruent to alpha naught mod M.
Okay.
I understand your confusion. See, Manav, I am trying to do two things. Okay. One is the trivial case is a corollary to this lemma, what you're seeing on the screen. This what you're seeing on the screen. Okay. There it is done because you're taking x minus alpha naught for g naught. Therefore, you will get some x minus alpha. And that is the property that alpha bar is alpha naught.
Yes.
That is fine. But now I am saying this is also a corollary to the Hensel's lemma in the last class, not today's class.
Okay. Yes.
There we have concluded that has a root we have concluded because mod f alpha naught is less than mod f prime alpha naught square. Therefore, that Hensel's lemma says it has a root alpha. Now I want to conclude this part. No. And I'm saying that also follows because in that lemma you had mod alpha minus alpha naught is less than or equal to that C. C was that quotient, and that quotient is something which is strictly less than 1 because of this assumption. Therefore, what you have is mod alpha minus alpha naught is strictly less than 1, which means alpha minus alpha naught belongs to M, which means alpha is congruent to alpha naught mod M. No confusion, no Manav. I am saying that this statement, I am deducing this from today's Hensel's lemma, and I am also deducing this from last class Hensel's lemma.
Yes, it's fine. I got it.
Okay, good. So both are generalizations of, and this is the official word. This is not my word. Lang says this is what is called the trivial case of Hensel's lemma. So if someone says the trivial case of Hensel's lemma, that means this simple situation. Okay, so many times this itself is good enough. This itself is useful, and you can directly prove this. Proving this is much easier than our earlier proof, because the Cauchy sequence that you can define a better algorithm. You can just take alpha I plus 1 is alpha I minus f alpha naught by f alpha I by f prime alpha I, and you can easily show convergence if you want only this much. Anyway, we have proved much more. Okay, here is an very useful application. Suppose K is a complete non-Archimedean field with residue field. So I'm assuming something more here. Okay, so I'm assuming that O by M is actually a finite field. So I think this is true if you assume DVR, maybe. No, I'm not sure. Anyway, assume that the residue field is finite. If it's finite, then it will be some prime power, right? So assume it's FQ where Q is a prime power. Under this assumption, you consider this polynomial x power Q minus x. Then this is the claim is that this has Q distinct roots in O. Why is that? By the way, so this Hensel's lemma that we have done for factorization into two polynomials is true for any finite factorization, no, by induction, right? If you can factorize into 2, you have got that statement, you have got the statement for 3, you have got the statement for any finite number. So that is okay. Now you consider x power Q minus x. What happens? So consider this as a polynomial in OX. And what happens if you reduce modulo M? If you reduce modulo M, it is the same polynomial, right? And how many roots does it have? So this means x power Q is x. That means x power Q minus 1 is 1. So these are precisely all the non-zero elements. I mean, these are precisely all the elements of FQ, right? X power Q minus x. Its roots are precisely in FQ. Its roots are precisely all the elements of FQ. Because all the elements of FQ you can characterize as x power Q equal to x. And these are distinct elements because you know that these are simple roots, no? Because what is the derivative? Derivative is Q times, Q times x power Q minus 1, which is 0 because characteristic is Q, characteristic is P, minus 1. So derivative is non-zero, so they are all distinct. Okay, so that's why distinct. Distinct roots in the residue field, and therefore by Hensel's lemma you can lift all of them. So therefore the conclusion is the polynomial x power Q minus x has Q distinct roots in O. This follows. This is an application of Hensel's lemma. All of you are clear with this? This is a very important statement that if you take the polynomial x power Q minus x, then it has Q distinct roots in O if you are in a complete non-Archimedean field with residue field FQ. Statement is clear, no? Residue field need not be finite, but assume it is finite, then it is FQ for some Q. Take that particular Q and consider x power Q minus x, the same Q, and then this has Q distinct roots in the ring of integers O. Okay, and this is slightly non-trivial. This is actually by Hensel's lemma. We are applying today's Hensel's lemma actually. Okay, so what have you got? You have got K and you have got O, which is a DVR, and not just that, the residue field is finite. So if you are in such a situation, then then you have got corresponding to each element of the finite field, you have got an element in your ring whose reduction is that element. So from your ring to FQ, from O mod M to FQ, you have the reduction map bar. So what you are saying is each element of this can be lifted uniquely. There is element X. If you have an element X bar here, there is an element X such that X bar is X bar. That's what you're saying. Is there a question?
Like,
Okay,
I was wondering, can we conclude this from the trivial lemma, trivial version of the answer?
Okay, let's do that. Yes, you can conclude from the trivial lemma also, I think.
No,
Well,
but we
I'm
need to
not.
check distinctness somehow, no? Like, corresponding to each root of x bar q minus
Let's
x in the quotient, we will
let's
get a
see,
root here.
Yeah, let's see slowly. So will it follow from the trivial lemma? Let us see at least one root can you lift using this, because f of you want after bar, right? So if you do bar, then it has a root, one root, and that one root can be lifted using the trivial case, right?
Yes.
Because f of alpha naught, f bar of alpha naught is 0 and f prime bar at alpha naught is non-zero. So one root can be lifted. One root can be lifted, and means this polynomial can be written as x minus alpha times a polynomial of coefficient q minus 1, degree q minus 1, right? Now can you apply the trivial case of Hensel's lemma to that polynomial of degree q minus 1? I think again you can, because that will be again monic, because if you take an x power x minus alpha, the q minus 1 degree polynomial, that's again monic, and that has a root in fq after reduction bar, and that also is a simple root, because this polynomial itself has all simple roots, so that also can be lifted. Yes, this follows from the trivial case.
Minus 1, why will it have a root in the quotient field?
Say that again.
The polynomial of degree q minus 1,
Yeah.
why will it have a root once you quotient it? Once you take it mod m, why will it have a
Yeah.
root?
Because the bar of that polynomial times bar of x minus alpha is the bar of this, no?
I see.
Right? Call this polynomial f equal to x minus alpha times g. So
Yes,
f
okay.
bar is, yeah, that's obvious. Yeah. So trivial case is enough for this. I don't need today's version. Okay. But today's version you can directly apply. Yeah. So just for this trivial case is enough. Yeah. So this is important, and so these are called, so these roots that you are lifting, the lifted roots are called the multiplicative representatives of FQ in O, and many places you might also see another word. Have you have you seen? So if I go to Google, you can see, no? You can see my screen, right? You can see my screen, no?
Yes.
Yeah. So there is. Have you heard this mathematician's name? Teichmuller, I think, German mathematician. Have you heard this name? Have you seen this name somewhere
No.
before? No.
No.
Okay. Anyway, so there is this famous mathematician, German mathematician, and in many places you will see instead of multiplicative representative the name Teichmuller left. Okay, because he is the one who studied this a lot. But I prefer this term. Okay, so if you see that Teichmuller left, that means exactly this. These are the multiplicative representatives of FQ and O. Okay, so now let's do something very minimal and then we will stop. Something which is much easier now. So I'm talking about, what is called a p-adic field, where this is the prime ideal P. This is a Gothic script P. This is not prime number P. Which we will finally be interested in that actually, but a bit more generally. So O is a DVR. I'm assuming discrete valuation, and maximal ideal is P. Why am I using the notation P and not M? because it's a DVR, right? In a DVR, you know that there is a unique non-zero prime ideal, and that will be the unique maximal ideal of the local ring. So I prefer the notation P instead of M because its unique maximal ideal is actually the unique prime ideal. And K is the quotient field of O, and we will assume K is complete with respect to the valuation obtained via O. And you know the valuation obtained via O, no? What is that valuation? Anything will be any element can be written as pi power r times something else, some unit, and the valuation is c power r, where c is something less than 1, and c you can choose anything between 0 and 1. Fix one such thing. So this is our setting. So P will be pi times O. By the way, this is also called pi. In LaTeX, you have to write var pi, VARPI. So P is pi times O, and valuation of pi is 1. So maybe I'm using this notation for the first time. What is the meaning of this? In C power R, VP is just that R. So VP of pi is 1 because mod pi will be C. That's our normalization. That's how we define the valuation long back, and valuation of pi is 1. And I will not write this P always. I will just write valuation of pi because anyway we have fixed this. There is only one P, and I will not write it always for ease of notation. So define P power R to be all those x in O such that the valuation is bigger than or equal to R. So P is valuation is bigger than or equal to 1. P square is valuation is bigger than or equal to 2. If you don't like the notation valuation but you like the absolute value, then that means x in O such that mod x is less than or equal to C power R, where C is that fixed number. You fix a valuation. Agree? So define it like this. Do you agree that these P power R's are ideals? These are ideals of O. Is it easy to check that this is an ideal? P is your unique maximal ideal. And is it easy to check that this is also an ideal? Do you see the proof already?
Yes.
Yes, because if you take x and y, then modulus of x plus y is less than or equal to maximum of mod x comma mod y. Both are less than or equal to c power r. So addition is okay. And if you multiply by some number with modulus less than or equal to 1, then modulus is less than or equal to c power r again. So these are clearly ideal. So check each of this is an ideal in O, and check this also, that these are all the non-trivial ideals of O. So I leave it as an exercise. Understand the claim? If you take any ideal in O, it is of the form P power R for some R. Any non-trivial ideal. You have the zero ideal, you have the full ideal O. Other than that, if you take any ideal, it is of the form P power R for some R, some natural number R. Okay, so please check that. It's an exercise, easy exercise. Easy, but if you are new to this kind of thing, it might take some time. But finally, it's easy. 1 line, 2 line proof. Okay, think about this. So these are all the ideals. Now let's do a little bit of topology. So for x in P power R, which means mod x is less than or equal to C power R, or valuation of x is bigger than or equal to R, you take the ball, open ball, this is your usual notation from real analysis, open ball with center x and radius mod x. And I claim that this is contained in P power R. Do you see why this is true? So if you take an element y in this, what do you have to show? You have to show that modulus of y minus x, assume modulus of y minus x is strictly less than mod x. You have to show that y belongs to P power R, right? X is in P
Mod
power
x
R.
is less than C power R.
Yes. Mod x is less than C power R. Less than or equal to maybe. Mod x is less than or equal to C power R. And you are taking y from this ball. And what is given to you is mod y minus x is strictly less than mod x. So mod y minus x is strictly less than C power R. But what you have to show is mod y is strictly less than C power R. Why is that true?
Mod y minus x is less than mod x, and mod x is less than C power R, less than equal to C power R.
Yes.
So mod y minus x will be less than equal to C power R. So
yes. So mod y is also strictly less than C power R. So that shows, so what is the conclusion? given p power r, given any element x in p power r, you are giving a ball, open ball with center there and some radius. Okay, so what is the meaning of this in topology? X is an interior point of p power r, right? Interior point meaning there is a small ball completely contained in that. So X is an interior point. So what you've shown is every point is an interior point. In other words, p power r is open in the topology given by this absolute value. So each of this p power r is open. Is p power r closed? P power r is closed is clear, right? Because it's less than or equal to, it's a closed condition. Modulus is continuous, no? Absolute value is continuous, right?
Yeah.
If xn goes to x, then mod xn goes to mod x. You can check that. So absolute value is of course continuous, and therefore this is a closed condition. Therefore p power r is closed, obviously, but not so difficult to see. It's also open. Okay, so each p power r is both open and closed. And do you see this filtration? O contains p square, contains p cube, etc. Why? From the definition. Because p square means valuation is bigger than or equal to 2, p cube is valuation is bigger than or equal to 3. So what is the containment? If valuation is bigger than or equal to 3, then the valuation is bigger than, no. Yeah, if x says that valuation is bigger than or equal to 2, then of course, what is the containment? I'm getting confused on basic things. So you want to say that p square contains p cube. So if you take something from p cube, you have to show that it belongs to p square. If you take something from p cube, then valuation is bigger than or equal to 3. And 3 is bigger than or equal to 2. Therefore, valuation is bigger than or equal to 2. Therefore, it belongs to p square. So you have this obvious containment. P containing p square containing etc. And what can you say about the intersection of all this? Intersection is 0. Why? Because if you take something from the intersection, that means x belongs to p power r for all r. That means valuation is bigger than or equal to r for all r, which means valuation is infinity. Valuation is infinity is same as saying it is 0. Okay. If you want to argue with modulus, what this says is mod is less than or equal to c power r for each r. So mod is becoming smaller and smaller and smaller than anything. So mod has to be 0. So that is 0. In other words, you can say that these sets p power r, they form a fundamental system of open neighborhoods of 0 in K. Do you know this word, fundamental system of open neighborhoods? Okay, S is missing. So please point out all these typos to me at the end. There is an S missing here. What is the meaning of a fundamental system of open neighborhoods? Given any open set, it will contain, so this is a fundamental system. So given any open set of 0, so given any open set containing 0, it will contain one such set from this sequence. Okay, and that follows from the very definition, so you can check. So they form a fundamental system of open neighborhoods, and that's a basic topological notion. Okay, some more very basic facts and then we will stop. So consider the following homomorphism of additive groups. These are ideals, right? P power r is an P power r is an ideal, and ideals are also additive groups under addition. So there's a natural homomorphism that you can check. If you take x in this, you multiply by pi power r. So x going to x times pi power r plus p power r plus 1. Is this a homomorphism? This is easy to check. This is a homomorphism. Is it surjective? Is this map surjective? So what will be an element? What will be an arbitrary element here? It will be y plus p power r plus 1. So y belongs to p power r. But if y belongs to p power r, then y can be written as pi power r times some x, right? It's a PID, unique factorization domain, therefore. So if y is in p power r, then valuation of y is at least r. So you can write it as pi power r times something else, which I don't care, something else in O. So y can be written like this, and therefore you have the pre-image x. So it is surjective. And what is the kernel of this map? What is the kernel of this homomorphism?
E power r
P power
P power
R?
R, right?
No. It
Sorry,
is
P, P,
bigger
P, P.
P, no?
Yeah.
Because you want x pi power r to be in p power r plus 1. So x is in p will do. Okay, so kernel is p. So this is surjective and its kernel is p. And therefore you have got basic isomorphism theorem. O by p is isomorphic to p power r by p power r plus 1 as what? As additive groups, as a group. So O by p is a field, no? O by P is a field because P is the unique maximum, P is a maximal ideal. O by P is a field, and but as additive group, this so the additive group of this field is isomorphic to each successive quotient. That's one observation as additive groups. And let's do one more thing and then we will stop. Okay, consider the units. So this was some additive group, as additive group, something we studied. Now we want to study some multiplicative groups. A natural multiplicative group is take the units of O, call it U, and I'm going to define a filtration there also. U subscript I is 1 plus p power I. What is the meaning of 1 plus p power I? It consists of elements of the form 1 plus x where x is in p power I. That's a set notation, 1 plus p power I. And do you see this? U contains U1 contains UI contains etc. Earlier we had p containing p square containing etc. And therefore if because p contains p square, 1 plus p will contain 1 plus p square. So U1 containing U2 containing etc. is done. But why does U contain U1? In other words, why is an element in this a unit? So what is a characterization of units? Unit is same as saying mod x equal to 1. So if you take an element 1 plus x, where x is in P, then what is modulus of 1 plus x? Modulus of 1 plus x is less than or equal to maximum of mod 1 mod x with equality if these two things are different. Mod 1 is 1, and what do you know about mod x if x belongs to P? Mod x is strictly less than 1. So you have 1 and something which is strictly less than 1, so they are unequal. Therefore, it's an equality in the ultrametric inequality. So mod of 1 plus x, if x is in P, is equal to 1. In other words, 1 plus x is a unit. So that's one way. Otherwise, directly you can show, because in order to show 1 plus x is a unit, what do you have to do? You have to show that it has an inverse. But what is 1 by 1 plus x? 1 by 1 plus x would be 1 minus x plus x square minus x cube plus etc. Where x is in P. Because x is in P, that infinite series converges and you get a number in O. So either way you can show that it's a unit.
We are still in a DVR, right?
We are in a DVR throughout, with this title periodic field, I'm in a DVR. That's why I use this title.
Then the valuation is slightly different, right? The like 1 minute. Like the maximal ideal is the set of all elements such that
Mod is strictly less than 1 or valuation is strictly bigger than 0. Or valuation is
valuation is strictly. Oh, okay. Yeah. Valuation and modulus are different.
Yeah. Yeah. So either you can say valuation is great. That's why I define here p power r. Either you can say valuation is greater than or equal to r, or you can say modulus is less than or equal to c power r, or you can say modulus is strictly less than c power r plus 1, c power r minus 1. This less than or equal to you can remove and you can put a strictly less by adjusting this r. So p will be modulus strictly less than 1 will be p. And modulus strictly less than 1 is same as saying less than or equal to c. You agree? The set with modulus strictly less than 1 is equal to the set with modulus less than or equal to c. Because it's because of the discreteness. There's nothing between 1 and c. There's nothing between c and c square. Right? If you are in integers, strictly less than 2 and less than or equal to 3 mean the same thing, right? No. Strictly less than 3 and less than or equal to 2 mean the same thing, right?
Yeah.
if you are in the set of integers, something similar because of discreteness. So like that also you can see this is open because this can be replaced by a strict inequality, and by the continuity of absolute value you will get openness. So yeah, so each UI is a group under multiplication. That's the next claim. So U is of course a group under multiplication. These are units. Units of course form a group under multiplication. But each UI is a group under multiplication. So what do you have to show? I have to show that if you take two elements from UI, their product belongs to UI. And if you take one element from UI, its inverse also belongs to UI. But these are all easy to check. If you take x and y in p power I, so if you take two elements, they will be of the form 1 plus x and 1 plus y, where x and y are in p power I. So you take the product 1 plus x times 1 plus y. What is the product? It will be 1 plus x plus y plus xy. In particular, it is 1 plus x plus y mod 1 plus p power I plus 1. But this is in 1 plus p power I, no? X is in p power I, y is in p power I, so x plus y is in p power I. It's an additive group, so it is in 1 plus p power I. So product is there. So it's closed under multiplication, and if you take an element in 1 plus p power I, you can write it as 1 minus x. And if you take its inverse, it is this power series, this geometric series, and this is convergent. 1 plus x square plus etc. is convergent. Why? Because the partial, the sequence of partial sums is Cauchy, and because of assumption of completeness, it will be convergent. Why is the sequence of partial sums Cauchy? Because if you take successive difference, it is x power n, and modulus of x power n is less than modulus of x power n is less than c power n. Modulus of x power n is less than c power n, and c is less than 1. So as n becomes bigger and bigger, that is very small. So it is Cauchy. Therefore, this converges. So this inverse exists in O. So 1 minus x has a unit, and 1 minus x has an inverse. So 1 minus x is a unit is clear, but I need to show something more. I need to show that this belongs to, if x is in p power I need to show that this also belongs to p power 1 plus p power I, and that is true because it is of this form, and this is x times some unit, and x is in p power I. Therefore, this is in 1 plus p power I. Is that okay? Was it too quick? The inverse is thus, this converges, therefore this is an element in O, and I am saying this is an element in 1 plus p power I. Why? Because 1 plus, so you leave that part, so you have to show that this element is in p power I, this infinite sum is in p power I, and that is true because you can take x common, and what is remaining is 1 plus x plus etc., which is a unit. So you are getting x times a unit, and x is in p power I, so x times that unit is in p power I. So this highlighted part is in p power I, therefore the inverse is also in 1 plus p power I. So 1 plus p power I is a multiplicative group. So you are getting a filtration, a descending chain of multiplicative groups inside the group of units. And all these are open. Why? U is openness, okay? Why is U open? Because U is the complement of P in O. And P is closed. Therefore, the complement of, P is closed in K. P is also closed in O. Yeah, you can check. P is also closed in O. See, one way to check that is O is closed in K, and a closed subset of a closed set is closed, no? So P is closed in O. Therefore, it is U is the complement of P in O. Therefore, U is open in O, and therefore it's open in K because O is open in K. So U is open, and each of the UI are also open. That can be seen directly from here because we have already shown that PI is open, and this is just a translate. And translate is a homeomorphism. Translation is a homeomorphism, right? Why is translation a homeomorphism? What I mean is plus is a homeomorphism. No, what I mean is plus a constant. That map f of x equal to x plus k, where x plus lambda, where lambda is a constant. That's a homeomorphism. Because that is continuous is easy to check because your topology is topology given by absolute value. You check that that's continuous, and if that is continuous, its inverse is also a translation. No, if f of x equal to x plus lambda, what is the inverse map? Inverse map is f of x equal to x minus lambda. So that's also a translation. So inverse exists and it's continuous, so it's a homeomorphism. So these are also open sets. Okay, and you can consider this natural map O to O by P. What is the natural map here? X going to x plus P. And check that units go to non-zero elements. If you take a unit here, the image is non-zero here. In O by P is a field and units will go to non-zero elements. Why is that? Because if x is a unit, then there is a y such that xy is 1. And where will xy go? Xy will go to xy plus p, which is x plus p times y plus p. So x plus p cannot be 0, right? Because 1 goes to 1. So xy is 1 and 1 goes to 1. So conclusion is x plus p times y plus p is 1. So x plus p cannot be 0. So units go to non-zero elements. And it's also surjective. So you get a map from units to the non-zero elements of O by P, the multiplicative group of this field. And this is surjective, that's clear. Because if you take any y plus p here, y is in O and y is not in P, therefore mod y is 1, so y is a unit. So that is surjective. And what is the kernel? What is the kernel of this map? The map is this, x going to x plus p. If you take a unit, then you will get a non-zero element. So what goes to 1? Kernel is those elements which go to 1. So what goes to 1? Yeah. This is the map. So what is the identity element in this group? It is 1 plus p, no?
Yeah, so 1 will definitely go to 1.
Yes. Anything in 1 plus p will also go to 1, no?
Yes.
And only that will go to 1. So kernel is 1 plus p. 1 plus p is what I call u1. Right? The kernel is those x such that x plus p equal to x plus p belongs to 1 plus p, right? No, x plus p equal to 1 plus p. That means x minus 1 belongs to p. That means x belongs to 1 plus p. So kernel is precisely 1 plus p. 1 plus p is what we call u1. Remember, ui is 1 plus p power I. So kernel is u1. Therefore, u by u1 is isomorphic to the non-zero elements of this field. So you have two important isomorphisms. One is as additive groups. You had O by P is P power R by P power R plus 1. For each R, this is true. And as multiplicative groups, you have U by U1 is O by P star. And similarly, for each I bigger than or equal to 1, you have the isomorphism Pi by Pi plus 1 is Ui by Ui plus 1, where the map is x going to 1 plus x mod ui plus 1. So you can check this, okay. So u by u1 is slightly different from u1 by u2 onwards. u1 by u2, u2 by u3, etc. are isomorphic to this. Whereas u by u1 is not isomorphic to O by P, but the non-zero elements in O by P. So there's a slight difference at the first stage and then onwards. Okay. So we will stop here today. Next class, we will show that all these are compact sets. O is compact, P is compact, P power R is compact, U is compact. Okay, so we will show that O is compact. And what will be an immediate corollary if we show that O is compact? If we show that O is compact, immediate corollary is this K is a locally compact field. Right? If O is compact, you have got a neighborhood of 0 which is compact. O is a neighborhood of 0 whose closure is itself, O is also closed. So O bar is O which is compact. Compactness we are yet to show. So once you show that, you can conclude that K is locally compact. So K is like, real numbers, complex numbers. These are all locally compact fields. So all these QPs also will be locally compact. So they are like very analogous to real numbers, except that they are Archimedean and these are non-Archimedean. We are showing slightly more generally. But compactness, yeah, O is compact will not be in this generality. O is compact will not be in this generality. It will not be in this generality. It will be under the assumption that O by P is finite. So I will assume O by P is finite. Already I made that assumption in this example, right? Under this assumption, we will show that O is compact. Okay, so we will do that next time and continue from there. So yeah, let me stop sharing the screen and I will stop the recording. And if you have any questions, you can ask me. Yeah, is there any